Hello, I am Alberto Tufali and I'm going to present you complex functions, multipole, and light polarization in a ferrocell. Uh, when a strong magnet is brought close to a Haller-Shaw cell containing ferrofluid, this magnetic fluid undergoes structural transitions due to the magnetic field, forming linear chains or rods of nanoparticles along the magnetic field direction. This is a magneto-optic effect in which an electromagnetic wave propagates through the ferrofluid that has been altered by the presence of a quasi-static magnetic field, forming some patterns like this one. For different uh, magnetic field intensities, we have this plot showing the light intensity versus the distance. So when we use this system with a polarizer and the light passing through this polarizer and passing through the ferrocell, we analyze this image with this another polarizer and we obtain patterns like this. Poles and vector fields. The representation of the magnetic field is a conceptual exercise that has generated several advances in physics. Since its conception with Faraday, helping to resolve contradictions involving actions at distance, for example. This work, we present the comparison between vector fields and magnetic fields involving the idea of light polarization in the ferrocell. We can see here some complex functions representing internal multipoles and external multipoles. The idea of multipoles with complex functions with negative exponents give these internal multipoles, and complex functions with positive exponents give the external multipoles. The internal multipoles can be obtained with this series for the magnetic fields, here for the case of a dipole, here for a quadrupole, and here for a sextupole. This is our experiment in the monopole, our experiment in the external multipole, our experiment in the external quadrupole. The internal dipole using the ferrocell give patterns like this that depends on the orientation of the magnetic field. The same happens with a quadrupole, that for the case of an internal quadrupole. Here, internal hexapole, and this one for internal decapole. We used Mueller matrix to simulate the intensities of the experiment, and basically Mueller matrix represents the Mueller matrix represents the magnetic field that is applied in the ferrocell. Here we can see some polar plots of a dipole in a sextupole or a hexapole, and the combination of these two gives the different light intensities if we combine different values for each one of these dipoles. So in this way, we can represent different uh, states of our system using a combination of different multipoles. For example, if we start with this system with a sextupole, and we change it a little bit this configuration from a circle to ellipse, we have the formation of these lines, black lines called isogyres. And when we change a little bit the magnetic field, these isogyres suffer some distortions, like we can see here. We simulated the intensity of the initial exapole, like this sextupole, and this is the simulation, and this is the experiment. Here, for the case of the quadrupole using Mueller matrices, and here we combined the intensities of this one. So this is the simulation and this is the experiment when we can see these 8 major lobes in both cases. Conclusions: in this work, we present our studies on how to represent different configurations of magnetic fields using complex functions, associating multipoles to the exponents of these functions that we classify as internal and external multipoles. Based on these representations, we built Mueller matrices to reproduce the polarization behavior of light when passing through a thin layer of ferrofluid in the device known as the Ferrocell. Thus, when these matrices operate on Stokes vectors representing linearly polarized light, we obtained parameters that can be compared with experimental results in our experiment. Here we have some reference, and thank you.